जाएंगे ना तो
এটা তো কোনো কেটিং এটা কি বল বন্ধ করতে নেই উপর থেকে ওটা না ঠান্ডা উপর থেকে দাও বেশি কায়দা দেখাতে গেলাম নদী কেটে গেল এটা একটু ফাটা দেখি করে হয় হাউ টু ইউজ ফাটা
Oh, hi, Peter.
Hi, Zijian.
Yeah, very nice to see you.
Likewise, you're at the West Coast. You're at the wrong place.
Right. So are you at your office?
Yeah.
Okay.
I have to run away actually at 4:05. So Sara, maybe I have to. She's here too. I can see her, but.
Yeah, don't worry, it's okay.
Okay, yeah.
You already
hi,
saw a
Sara.
version of the talk. Hi, it's fine. Don't worry.
It's great that this is happening. It's cool. I'm sure I will miss Niklas' discussion, so sorry, Niklas.
It will be a great discussion, Peter. But it's the part you can cut, I guess, if you miss something.
Maybe if you all agree, we start, because we're already 4 minutes after. Xinwei, are you there? Oh, great. Fantastic.
যাবো যদি করো তাহলে যাবো না তো একটু বাদে যাবো
Okay, so hello everybody. This is a novel edition of the YoungStatS One World YoungStatS webinar series. This is the first joint webinar with the New Researchers Group of the Institute of Mathematical Statistics, IMS, and the Young Data Science Researchers Seminar, Zürich of ETH Zürich. I will initially thank greatly to Professor Peter Bühlmann, who is here, also to Pragya Sur, president of the New Researchers Group of the IMS, who initiated also these webinars, provided ideas. I also thank all the colleague organizers from the Young Data Science Researchers Seminar Zürich, or all of the team, I think, is here. So the webinar, generalization and causal inference. So when we decided on the topic, we wanted something advanced related to data science, which will be the ground topic of our webinars. What you will hear are 2 great presentations related to contemporary methods in causal inference, to invariance and to distributional shifts. They will be discussed by Dr. Niklas Pfister of University of Copenhagen, who provided us great help in the organization of this webinar. For more, I give the word to Xinwei Shen of the Young Data Science Researchers Seminar Zürich. We will jointly moderate this webinar. Thank you.
Okay, thanks, Andrej, for the nice introduction. So now let me introduce speakers. So our first speaker is Zijian, who is an associate professor at the Department of Statistics at Rutgers University. So he obtained PhD in statistics in 2017 from Wharton School, University of Pennsylvania, under the supervision of Tony Tsai. His research interests include high-dimensional statistics, causal inference, multi-source learning, and non-standard statistical inference. And our second speaker is Sara Magliacane, who is an assistant professor in the Informatics Institute at the University of Amsterdam and a research scientist at the MIT-IBM Watson AI Lab. In the past years, she has been working on causal discovery from different experimental settings and on methods to design experiments that would allow one to learn causal relations in a sample-efficient and intervention-efficient way. Her current focus is on causality-inspired machine learning, applications of causal inference to machine learning, especially transfer learning and fast adaptation in reinforcement learning. And last, we will have our discussant, Niklas Pfister, who is an assistant professor at statistics at Copenhagen Causality Lab, Department of Mathematical Science at University of Copenhagen. His research focuses on statistical methodology for complex data structures, often involving notions of causality and stability to model and infer the underlying causal mechanisms. Okay, so now maybe let's get started with our first speaker. So Zijian,
Yeah.
I will pass the mic to you.
Thank you for the introduction. So just a quick question. Do we need to record this? Because I don't see a recording running on.
Yes, I think so, Andrej.
Oh, okay, okay. No worry. I just
Yeah, thanks for.
Just a second. Apparently, it stopped when I went out.
Yeah.
It is like there is no worry, but you just need to permit it. Thank you for noting.
Is it good? So can you see my?
I think you need to just to say that you allow it.
Okay.
Just a second. I will reclaim the rights and
okay.
just a second. Aha, it's good. It's
Okay.
Thank
Okay.
you.
Yeah.
Thanks.
Yeah. Thank you. Give me 1 second. Share my screen. Yeah. So you can see my screen and it's also full screen.
Yes.
Okay.
It's not full yet. Now it's full.
Yeah. Okay. Okay. Yeah. Thank you. Yes. Thank you, everyone. Thank you, the organizer for organizing this very nice like webinar event. And thanks everyone for coming. And it's really my honor to talk about this. And it's especially like this is connected to the Zurich team because I learned all of the things when I visited Peter in 2018. So I think it's great. I talked to the right audience and about this something I feel interesting. I have learned during my visit. So I'll talk about this statistical inference for the Maximin effect, so which is a very novel idea introduced by Niklas and Peter in their 2015 IMS paper. And I'll talk about some of my own thinking along this line. So let me first, okay. So here is
one of them where
so here is the outline. So I'll first talk about
some developmental factors of some
sorry.
maybe
Okay.
use
Please unmute yourself, please.
that data set, and then she mentioned something about another one as well. So
Okay, so let me try to mute.
yeah.
谢谢，这比海底捞要奢侈了。
Okay, yeah, sorry.
I hope it will work.
Okay.
Now.
So yeah, let's get back. So this is actually the outline. I'll first introduce what's the model, and then I'll talk about identification, method, theory, and I will show you some numerical results. So first, let's look at what's the setting we are looking at. So we look at the multi-source learning. So multi-source learning, we can just use this example to look at what's the data set. So we have the institution one.
Zijian, I think you hasn't started screen sharing.
Oh, okay. Give me 1 second. Sure. How about now?
Yeah, perfect.
Okay, sorry. Yeah.
Just make it full screen, maybe.
Okay. Now it's full screen, right?
Yes, it is. Yes.
Okay,
Great.
let me continue. Sorry for that. And we have different institutions, institution 1 to institution 4 as this like the cartoon illustration. And our goal is for the institution 1 until institution 4, we collect this outcome data, the covariance data. And our goal is to make a good prediction model for the target institution. So which is for example, a new hospital, we want to make some very nice prediction in the future. And for this new hospital, for this target population, target institution, maybe we do not have as much information as for example, we do not really observe enough outcome for this target population. In this case, we have just to go with like partial information, for example, just the covariance from this target institution and to construct the prediction model. Okay. So a little bit more details, like what's the challenge for the multi-source learning? Like I have just demonstrated using the previous cartoon picture. So the biggest challenge is the data heterogeneity. So maybe due to data from different subpopulations, different healthcare centers or different environments, the distribution of the data, they're just different. And there are some distribution shift. And there are already a lot of literature about how to do this model averaging across different sources. For example, we can just merge the data, or we use a standard meta-analysis approach, such as inverse variance weighting, or we use some recently developed federated learning approach. But a main issue for a lot of this model averaging method is that they assume that the data heterogeneity is not that severe across different sites. So for example, a lot of them just assume that the model across different sites, they are very similar, and which is actually not ideal for real applications because the data can be quite heterogeneous in many applications. Okay, so for today's focus, I'm going to talk about the Maximin effect, which is shown to be a group distribution robust models, and that's today's focus. And for such a model, it actually has two advantages. The first one is heterogeneity. So it allows that the different sites have different distribution. They allow to have different distribution shifts across different sites. And the second one is generalizability. So we know that all of the sites have some difference, but they also have some similarity. So we try to use this Maximin effect or the group distribution robust models to capture the stable associations shared across different sites. So that's the main advantage of this group distribution robust models. And let me start introduce some mathematical notation and also the definition of the group distribution robust models. So we use some basic notation for the L set. We use PXL to denote the covariance distribution and the PLY given X to denote this conditional mean outcome model for the L set. And for the target population, we use QX to denote the covariance distribution and QY given X to denote the conditional mean model. And some important remarks about the setting. So we assume that there's basically no observations for the target population. So this is the case for a lot of applications. We just do not have enough observations for the target population. And here we consider extreme case, we have no observations for the target. And second, we allow that it's a PXL and QX to be different. So we allow the covariance shift. And most challenging, we also allow this QY given X is different from PYXL. So we allow this kind of posterior drift. So conditional outcome model, they are also different. So if you think about in this setting, actually identifying QY given X is impossible because we have no outcome observation for the target population, and we do not assume kind of similarity condition between the PL and Q. So how can we learn the Q? So in this case, we actually cannot really learn this model Q, but instead we adopted some literature results to introduce a new robust model that we are going to target at. So which I'm going to introduce is the distribution robust models. So this is the figure I have just shown. And let's imagine, so there's a target institution. And for target institution, we really do not know we know it's covariance distribution because we know we can observe some covariance, but for the outcome variable, we just do not observe it. And we do not know the conditional outcome model. But instead of saying there is a given conditional outcome model, we're considering a class of conditional outcome model. So we use a T to denote a class of conditional outcome model. And specifically, we consider this T is a mixture of the PL, which is the conditional outcome model for the source population. Okay. So this CQX, which is a class of distribution, is actually saying that for the target institution, we do not really know its distribution, but instead of looking at one single distribution, we're looking at a class of distribution. And the class of distribution fixing the covariate distribution at QX, but the outcome model as a mixture of the conditional mean model of all of the source institutions. So this is the uncertainty class, the CQX. So with this uncertainty class, we are going to define the group distribution robust models, so which is defined as follows. So for X and Y, assume that they follow a distribution T. Then in this case, we can define a reward function for linear prediction model beta. And this is the formula computing the variance explained by the regression model beta. And for a given target distribution T. But now, since we have a class of distribution, we don't know which distribution the true target population comes from. So what we do is, instead of using one reward, we take the worst case of all rewards. So for any T belonging to the distribution class, we take a minimum of the reward, and we use this as our reward function, which is the worst reward function. Okay. And our goal is we just to try to maximize the reward function, but instead of single reward, we maximize the worst reward function, and that's the beta star Q, which is our target. And it's we call this group distribution robust models by adopting this the definition from this paper. So they introduce the group distribution robust models for the neural network, but now we consider a simpler setting, a high dimension regression or standard low dimension regression. Okay. So if you look at this, there are two interesting remarks. So the first one is when this CQX, if we just assume that CQX just contains one distribution instead of a class of distribution, say that just contain the target population, target distribution, then the beta star Q is reduced to the empirical risk minimization, like our favorite least square estimator. Okay, but now since we really do not know what's the target population, we use a class to define this the loss function. So that gives this distribution robust models. And the second remark is why this is called distribution robust. It actually comes from how do we define the reward. So when we define the reward, we are not just for a single target population, but we actually look at a class of distribution, and then we make sure that we construct a prediction model that works well for a class of distribution, not just a single distribution, and has a robustness. Say in the future, if we see a target population, it's maybe some perturbation from the source data, and we can still kind of pretend this robustness. Okay. And here's the connection. So if we assume that the PLX and QX are the same, no covariance shift, then actually this distribution robust model is just the Maximin model, which is already introduced by Niklas and Peter in their 2015 annals paper. And this is called Maximin because they take a minimum of this L class reward and then they identify a beta vector to maximize this reward. Okay, so that's the target. And as I mentioned, so this beta star or beta star Q is nothing related to QY gamma X. It's not the true model, but instead, this is some model we compromise. We really cannot identify the true model, but we try to identify this condition, like a distribution robust model. Okay, and also this distribution robust model have some nice property I'm going to introduce. Okay, so let me continue. I'll first talk about how do we identify this. So when I first learned this from Peter's paper, the first question in my mind is, this seems to be a complicated thing. Like we need to first take a max and then do a minimum, and how can we really identify it? And this is there's a very beautiful theorem from Peter's paper and also Peter and Niklas' paper, and also I extend that to this distribution robust, group distribution robust model, slightly extended. So let's just make some additional assumption. So for all of the source data, we assume that the relation between Y and X is actually a linear model. So which is captured by the regression vector BL. And the BL will allow it to change with the index L. So from set 1 to set L, they can have different BL. Okay. So if we make this assumption, then actually the Maximin effect, as I have defined, or the group distribution robust model as I have just defined, can actually has a very simple and elegant form. It can actually be written as a weighted average of BL. Okay, so forget about how do we compute the weight, but just look at the expression. So it gives a very nice interpretation. So it's a linear combination of weighted average, and second of all, it give us a way to do the computation. Okay, we can compute a BL, and then we just do a weighted average, and that's will give us this distribution robust models. Okay, and then let's look at how do we compute the weight. So we compute the weight can actually be computed by an optimization problem, like by gamma Q, and the do an optimization problem with respect to the simplex. Okay, and what's this gamma Q? So the gamma Q is actually the regression vector covariance matrix. So the gamma Q LK, it measures the correlation or the covariance between BL and the BK weighted by the sigma Q. And the sigma Q is variance covariance matrix for the target population. Okay, so this actually gives us a very neat way of identifying the Maximin effect. And this is an important figure. I basically replot them from Niklas and Peter's paper. So what's the geometric meaning of the Maximin effect? So actually the geometric meaning is the Maximin effect is capturing the stable association. So let me illustrate with this two-dimension case. So this is the two-dimension case, and each regression vector is just a two-dimension regression vector. And we got different sites that's represented by the black dot. And the Maximin effect, or the effect we have just shown in the previous slides, you can actually identify it as, and we draw a convex hull of all of these regression vectors, which are heterogeneous. And the Maximin effect is the one lying on this convex hull and closest to the origin. Okay, so this is a very nice property. It says that we have heterogeneous effect, and Maximin effects summarize it. And it represents a stable association. That's the one closest to the origin. Okay, and the interesting part is on the right-hand side. So in this very special case, like the beta 1 is shared across different sites, but beta 2 is kind of have heterogeneous effects. For some sites it's positive, and for some sites it's negative. And in this case, we can see that if we apply the Maximin effect, then actually it shrink all of the heterogeneous treatment effect to 0. But keep the beta 1 to be non-zero. Okay. So far we have talked about what's the group distribution robust models and what's this identification, like how do we identify that? And when I got to this part, I have a question in my mind. So the question is, let's think about we have a two group case. For the two group case, we just need to compute like one weight, the other one is just one minus it. And we, fortunately, we have the explicit formula. And the gamma Q is a regression covariance matrix. And let's just use the most intuitive way. We use the gamma hat to estimate the gamma Q. And you can imagine the gamma hat is a very good estimator. So it's an unbiased asymptotic normal. So whatever good property we can assume. But even in such a case, the gamma hat 1 is not a good estimator of gamma star 1. Let me point out two cases. The first one is non-regularity. Non-regularity means if this true parameter is close to 0 or close to 1 due to the truncation. So this gamma hat 1 is actually not will not be a asymptotic normal like near gamma star 1 due to the truncation. It will be a mixture model. And the second one is instability. So when we do this computation for the gamma Q11 plus gamma Q22 minus 2 gamma Q12. So if this quantity is very close to 0, then no matter how we estimate it, like how accurately we estimate it, because we take 1 over that, so that will cause an instability issue. So that's the second challenge. So just because of this two challenge, so even though we know how to identify this Maximin effect, population-wise, finite sample-wise, how to quantify its uncertainty has become like extremely hard. And let me just give you a data illustration. So on the left, I got this instability. You can see that the weight supposedly should near 0.5, but it spins around 0 and 1. Basically, there's just no concentration of the weight. We cannot estimate well. And as a result, so the average, the Maximin effect we compute has a big bias. Okay, and similar on the right-hand side, due to this non-regularity issue, the weight has a truncation at the left-hand side. And due to this reason, the Maximin effect like has a bias. Okay, so that's give us the challenge. Like when we do the Maximin effect, if we just do the plugin estimator, we will have an issue. And how can we quantify the uncertainty of the Maximin effect? So let's look at this estimator more closely. So let's say our target parameter is a Maximin effect, do a linear combination. And by the identification result we have reviewed, so beta star is actually a weighted average of BL. So we can write it in this form. And a simple estimator is we just estimate a gamma hat and estimate X new transpose BL. And then we plug in them. So that will be the plugin estimator. Okay. And we can easily show that this X new transpose BL hat is a asymptotic normal and unbiased, saying in low dimension, you can just use a least square estimator. Okay. So the challenge is from the right part. So when we compute the weighted average, so even though the regression covariance matrix we estimate very well, but when we compute this gamma hat as the minimizer of this optimization problem, as I have just shown that this gamma hat does not have a standard distribution. It could be like a mixture distribution, or could be like very unstable spin between 0 and 1. Okay, so this is a very long-standing problem in statistics. It's called the nonstandard inference, and we just cannot apply our favorite central limit theorem to construct confidence interval. And unfortunately, when we do this Maximin effect, do the uncertainty quantification, we face this challenge. Okay. So here is one solution. So we're using some resampling method to solve this non-standard inference. So the gamma hat Q is a regression covariance matrix. We can estimate and we can show that it's roughly mean 0 and asymptotic normal with this variance covariance matrix. So what we do is like a parametric bootstrap. We centered as our estimator and using the variance to do the resampling of this gamma hat M. And we enlarge the variance slightly for technical reason. So for each of this capital regression matrix gamma hat M, we can do optimization to compute this gamma hat small m. Okay. So if the capital M is equal to 1000, then we just compute 1000 this weight vector. And that's the resampling idea. And if you're interested in this kind of resampling thing, I think it's the more accurate name. It should be some confidence distribution instead of parametric bootstrap. Okay, so that's where the idea is from. So after computing this related weight vector, so we need to leverage this related resampled weight vector. And here is the property we are going to use. So the gamma hat is the estimator, the point estimator we'll have just using the raw data, and gamma star is a true value. And after resampling, we have a lot of this green points. That's the gamma hat M. So we can show that there exists at least one of this gamma hat M star, which is fairly close to the true value. So that's a sampling property I'm mentioning. So it means that after resampling, at least once we are lucky, and we can basically recover the true gamma star. And use that, we can actually quantify the uncertainty of the weight vector instead of using this asymptotic normality. Okay. So for each of this weight vector, we can do a related average of this X new beta hat M. And for this lucky M star, if we do error decomposition, there is one part is from this gamma hat M star and the other part is from X new transpose BL. And we can actually see that from the previous plot. So the first term is actually negligible because the gamma hat M star is fairly close to gamma star. And the second part is actually the part like the randomness comes from. We just need to quantify the uncertainty of the second part. Okay. So based on this intuition, for each of the resampled data or resampled M's time, so we can construct a confidence interval by just quantifying the uncertainty of estimating X new transpose BL. Okay. And we got M of such interval and we take a union. So that's our final confidence interval. And here is a illustration. So for each of this x-axis, it means the sampling index. So we can see that we got the different confidence interval. And we take a union, it's a right interval. And this green one is actually and it's not a benchmark, but it's the one like we assume there is a asymptotic normality, which is probably not the case here. And I just want to show you that the right one is not super long comparing to such a asymptotic normal estimator. Okay, so that's our proposal. And also, I just want to mention that at some point, I think, okay, we cannot have parametric length confidence interval, but fortunately, we show that the interval, even though the right interval is a little bit longer, so the interval is still for parametric length, and you can track the paper for the proof. Okay. Oh, okay. Sorry. So how much time do I still have?
Probably a few minutes, 5 minutes maybe.
Okay. Okay. So let me show you some numerical results. So we compare with the asymptotic normal interval, which is have the point estimator and have this 1.96, the quantile, and get the standard error computed by in Oracle ways, like we write 500 times and we can compute the standard error in this way. So this is something we'll compare to because there's not much method we can compare to for especially in the high dimension setting. Okay. So you can track the paper for detailed setting, but just want to give you an idea. So I1 to I6, those are settings like we got instability and the irregularity, those very non-standard inference setting. And I7 to I9, they also challenge setting. That's the irregularity setting. And I10 is a very nice setting, like asymptotic normal holds, and we can just use asymptotic normal to do the confidence interval. So as I have shown here, we can see that if we just using asymptotic normality, then actually the coverage is not good. But using our proposed confidence interval, it's slightly over covered, but the coverage. Oh, sorry. So you can you see now?
No.
Okay.
No.
Yeah. Okay. No.
No.
Sorry. I think someone joined.
Could you please reshare? Could you please reshare?
Okay. Sure. Let me do that. Okay. Yeah. Now it's good, right?
Yes.
Okay.
Please mute yourself. Oladapo, please mute. Thank you.
Yeah. Thank you. So we see that asymptotic normal interval doesn't work, but our proposed one works. And also, we're curious about the length. And if you look at the length, actually,
meanwhile, our service will.
Zijian, could you please mute Oladapo? You're the host, and Jean, if possible.
And program options, three options.
Mute. Okay, but it's still.
Physics, two options. Energy.
Okay. Yeah. Sorry.
Thanks.
Yeah. Okay. Yeah. I hope I don't mute myself. Yeah. Okay. So we compare the length and we see that the length is at most twice longer. And for the very nice setting, like the asymptotic normal works, and our length is like 1.35. So we do sacrifice the length, but the coverage is better. Okay. Yeah. So for this slide, we try the setting for low dimension, very similar setting, and we compare with the M-auto and bootstrap or M-auto and subsampling. So I just want to use this slide to point out something like there is a misbelief in the literature, like the subsampling or the M-auto and bootstrap method will solve this non-regular inference problem. It's actually not. It's slightly better than asymptotic normal, but it really doesn't solve the problem. So I'm not the first one realizing this. So this very elegant paper published in Econometrica, 6 pages, and tell the story very completely, gives examples that why M-auto and bootstrap doesn't really work for this setting. And I just use some numerical example to show you that the coverage really doesn't work well. So and for our proposed method, it still works, but again, it overcovers. Okay. So finally, we try some numerical study. We study like the East colony size, the relation between that, and also the genetic markers. So the dimension is 500, and the sample size is around 10,000. So 1,000, and we use 4 training media. That's the different media we're going to grow the yeast. And we'll look at like across these 4 different medias. So what can we learn between the relationship between the colony size and the genetic markers? Okay. So this is the first figure. I try to use this figure to show you the stable association that the Maximin effect has captured. So if you look at here, so for the SNP 420, so that's a SNP located on a very critical gene. And we can see that across the full training media, so it has a very significant negative effects. And then actually the Maximin effect is actually captures this like very strong effect, very strong negative effect. We can just look at this red interval. Okay. As another example, so like for this one, there is some cancellation. So some positive effect in some media and some negative effect. And we see that Maximin effect actually can detect that. Okay. And for the last one, like just no effect across all media. And we see that the Maximin effect is also like detecting that, just no effect. Okay. So this shows that Maximin effect is basically capturing this stable association, and hopefully those stable association, like they may have some causal meanings, but definitely we do not try to interpret the causal here. Okay. So this is, we apply this, the Maximin effect, our inference method, and we applied FDR control after each point, after each SNP, and we identify which SNP is like Maximin significant. And so we also tested the significance across seven test media. So in total, we got 11 media. So the main message of the picture is like those right ones, that those are detected by the Maximin effect. They are very replicable. So if you look at the Maximin significant effect, or Maximin significant SNPs, so they are basically like replicable important across all many different medias. And the 423 and 473 and 444, it's a same thing. And if you just apply, say, pull over the full source data and running the empirical risk minimization, you will see very misleading results. So they identify SNPs that not significant in any media. So I try to use this figure to highlight that the Maximin effects is identifying things that's really replicable even for a new environment. Okay. So I talked about this idea to Tianxi, and she feels this very interesting. So we try to apply this to a co-wide study, and we analyze this real data sets from 15 healthcare centers across the world. And we designed a serve Maximin algorithm, and it shows like a very nice prediction performance in that application. And also we try to make the algorithm privacy preserving. So due to my lack of expertise in this data, and maybe you can track the paper and see more details. Okay. So finally, I would like to do a take-home message and wrap up. And then, we studied this multi-source data, and we emphasize the heterogeneity, and we try to account for that. But meanwhile, we try to construct a model which is generalizable. And of course, another thing is this privacy preserving. I haven't talked about much. And one dimension I have added to this part is the non-standard inference. When we deal with multi-source learning, actually, a lot of cases we may face non-standard inference. Asymptotic normal doesn't hold. And how do we do that? And this is a resampling method. And also, I've mentioned this the Maximin effect introduced by Niklas and Peter, and also I connected with this group distribution of vast models. I think it's a very nice model to make inference for. Okay. So lastly, I want to thank Peter, Tianxi, and Niklas and Minge for their tremendous help with this project. And without them, I don't think I can write this paper. And I got a lot of insight from them. And also, I would like to thank my students and my friends. They have been having me read this paper. And here's a reference for the paper. And also, we have our package. And thank you very much.
Fantastic. Thank you. Xinwei will introduce the second speaker, but based that we don't have any question yet, just one short question, maybe flawed, but did you study in this context also the issue of efficiency? You mentioned asymptotic normality and unbiased and consistency. Does efficiency also make sense in this context of the estimator?
Yeah, yes, it makes sense. So I didn't start efficiency. I think it's a very important question, because the sampling method basically we lose the efficiency. You can see like in this asymptotic normal host, then asymptotic normal, probably we can use that as a benchmark, and our interval is like 1.3 times longer than theirs. So I guess the efficiency is not achieved here. So there's definitely room to work on efficiency, and also to figure out what's the efficient estimator. or what's the efficient like confidence interval. Yeah.
Okay. Thank you. Thanks
Yeah.
again for great presentation. Xinwei, maybe if we introduce the second speaker, Sara.
I think it's okay. I was already introduced before, so. Okay.
Xinwei, are you there?
Yeah. Let me know if you can see my screen.
Yes.
So you should see my iPad, so you'll see the same view I see, so it will be a bit weird, but hopefully it will be useful. So I'm Sara Magliacane. As we said, I work at the University of Amsterdam and also at the MIT-IBM Watson AI lab. And today I'll talk to you about this causality-inspired machine learning, which is something I'm trying to make a thing. We can argue if it's a thing or not. And it's the idea of using causality to help improve the robustness of machine learning. And obviously this was joint work with a lot of other people. And so you'll see in the papers that I will talk about. First, I wanted to start with a bit of a teaser. So it's a bit of a contrarian view. By the way, let me know if you cannot hear me or anything is wrong, okay? Is everything fine?
As well.
That's it? Okay, good.
Maybe
So I will...
if you put this full screen, Sara, I think there is something at the top.
Yes, I think I'm also happy with this, you know, it's fine.
Yeah,
I think
it's okay.
I prefer it like this because I want to be able to switch if I draw or anything else. So I'm still more of a computer scientist, so I'm always a bit scared by statisticians. So I'll give you like the causal hierarchy that we use, for example, in computer science when discussing causality. So this is by Judea Pearl. So the idea is that most machine learning, at least until recently, was working more at the level of correlations or association. So the first causal level of the causal hierarchy. And instead, causality cares about interventions and counterfactuals. And so I'm going to argue that sometimes, what I say, full causality, and this is, you know, a contrarian view, sometimes full causality may not be necessary, or it may be too expensive. And in this case, I mean that we may need, for example, too many experiments to be able to identify the causal graph when we do causal discovery. Or if we are going to try to learn causal factors from high-dimensional data, for example, in this case, images, you may still need a lot of assumptions. So I'm going to talk about, quote unquote, causality-inspired, which is like causality light, which will be somewhere in the level between association and intervention. So we're not going full causality yet. And I will explain what I mean more in detail. And specifically, we'll talk about one of our works on domain adaptation and some more recent works. But I just wanted to say there is a lot of work that could be called causality inspired. So we choose this causality to improve machine learning in many ways. So I'll give you this kind of little teaser example about causality versus transfer learning. I'm going to say that transfer learning is the problem of predicting what happens when the distribution changes. For example, if you have a self-driving car and the self-driving car is trained, for example, in US, you also want to deploy the self-driving car to be able to drive correctly in UK. And in UK, people drive on the other side of the road. Let me actually admit there is somebody who wants to be admitted. Just a second. How do I? Sorry about that. I'm just trying to figure this out. Okay, so somebody was just admitted. Okay, good. So transfer learning, we want to see what happens when the distribution changes. Well, in causality, we also want to see what happens when the distribution changes. Specifically, we want to see what happens when we do an intervention. And there is a lot of work on perfect interventions in which you essentially make the variable that you're intervening on independent of the other variables. For example, the do interventions also fix a certain value. And there is something called the do calculus by Pearl, but there is also a lot of other things. I'm admitting other people. But there is also this other thing called soft interventions. And soft interventions are the idea that you can change the distribution of a variable x given its parents. Yep, just a second, I'm going to mute a few people.
Yeah.
Sorry, guys, muting you. Okay, Good. Andrej is still unmuted, but the others are muted. Good. Okay. So we're here. Okay. And as you can imagine, these soft interventions, which just mean that we're going to change the distribution of a variable x that we're intervening on given its parents. They can be very general. And I'm going to say that we can use this also for things which are not quote-unquote real interventions, but for example, just the distribution of a variable given its parent changes in a different context. And so there is a connection between, for example, causality, especially when dealing with soft interventions, and transfer learning. And just to give you an idea why we even care about transfer learning, I wanted first to talk to you about this example. So I have a lot of machine learning examples, be warned. So the first machine learning example we have is that people were trying to solve this problem of visual question answering around 2016. And in this case, visual question answering is you have an image like this. You have a question, what color is the jacket? This is the jacket. And you have a few options in this very simple example, red and blue, which it is here, yellow, black, or orange. So this is one example. There are other examples. You have another image, how many cars are parked. And so here, apparently, there are 4 cars, etc., etc. So you have a data set with these questions. And what was happening is that people were convinced that, in 2016 already, the algorithms were actually quite good. And what happened is that Jabri et al. Actually tried a very simple test in which what they did is they threw away the images. They threw away even the questions. They just focused only on the answers. And essentially, they were just learning the statistical biases which happen in this data set, the standard data set that everybody was then using for visual question answering. And so they got very simple results just by training multi-layer perception on the answers only. Because, for example, most of the questions had, for example, most of the pictures were taken during the daytime. So if you have a lot of answers and one of the answers was daytime, you could just bet on daytime and you would be mostly right. And there were these kind of biases and imbalances in the data. So in a sense, the algorithms which were working so well, they were picking on spurious correlations. And that's why I think we should be using instead more sophisticated methods, for example, based on causality, which can maybe disentangle these things. And as I said, this connection between causality and transfer learning, it's not my idea. So people have thought about this. And for example, this is a paper already from ICML 2012, in which many of these people have already noted this connection. And I wanted to say as well, again, not just my idea, the idea that causality allows us to reason systematically about distribution shift, it's an idea that is presented in all of these different papers. And you can see recurrently the name of Peter around. So I was trying to sample a few different groups. There should be also some works from Niklas somewhere around here, definitely. If they're not here, it's just because I'm a bit lazy and this is an old slide. But so just that many people are thinking about using causality for distribution shifts, and that's why we have this slide. And Zijian should be here as well. And obviously, I selected the ones that I liked more because I'm a graphical models person. So I did have some selection bias in these papers that work with causality and distribution shifts, and I selected the ones which have graphs. Let me just admit again, another person. Okay. And as I said, many, many more papers. So this is just a completely biased sample. But just to say, it's not just us thinking about this. And this means we can reason about distribution shifts in causality through graphs, even if we don't know the graph, and even if we have missing data, and even if we don't care about reconstructing the graph. And so these two things are something we did in one of our papers, and I'm going to talk about this, but this is becoming, as I said, a growing area of research, so other people have also worked on that. But it's just easier if I explain to you first how we can use graphs, then I'm going to explain to you about this paper, and then I'm going to show you some newer results, because this paper has also a lot of issues that I will explain. Okay, first, I'm going to talk about unsupervised domain adaptation. This is actually the setting that Zijian already mentioned, I think, with a much more mathematical formulation than mine, but just to give you an idea. So we have data from some domain. In this case, we had some real world example with some mice. So we had wild type mice. So each row was a mouse, just a wild type means not genetically modified. We have some measurements of the phenotypes, X1, X2, and Y. Y was our label, X1, X2 were our covariates. And then we had essentially data from another distribution. In this case, we have mice which had been genetically modified. and we wanted to predict the label for these mice from their covariates, but we had no label for these mice. And this was what we call the target domain, similar to what Zijian actually already mentioned. The problem is that in general, we don't know what happens in the target domain, distribution shifts. So we essentially need some assumptions, otherwise this is impossible. And so it's called unsupervised because we don't have any label in the target. And from a graphical perspective, we're trying to do this from a graphical perspective, which, by the way, as I mentioned, people have already done since 2012 or 2013. And the idea is we're going to add the dummy variable, an indicator variable C, to all the data which are, for example, 0. So 0, sorry, for the wild-type mice and 1 for the genetically modified mice. Then we're just going to smash the data together and pretend they come from the same distribution, x1, p of x1, x2, y, and c, the c that we have added. And then we'll assume that this data here, there is an underlying causal graph that generates them, for example, this one. And we may or may not know the graph. And so in this graph, if you know a bit how causal graphs work in the Perlian framework, you would have that x1 causes y, and y causes x2. And y is what we care about, the label we try to predict. And the c variable that we just added also appears in this graph, almost as if it was a normal variable. And it means that the distribution of x1 shifts and the distribution of x2 shifts. Okay, maybe can we disable the waiting room because people are entering and I have to admit them one by one. Let me try to actually do that because otherwise I'm just admitting people one by one. Is it okay, Andrej?
Yes, everything seems okay. Yeah.
Okay, now people can enter without waiting room. Better.
Thanks.
Because otherwise they wait and I'm I get distracted. Okay, sounds good. Okay, so now step one, we know the causal graph. We really don't really know the causal graph. I'm just saying we know it so I can show you how it works. And then when we go to the step 2, we don't know the causal graph. And so we're talking about something called separating features, which I think other people have called, I think Niklas has also worked on that, and Peter calling stable features or invariant features. So essentially, people have been rediscovering the wheel, especially, I think we have been rediscovering a bit the wheel from other people. So in this case, the separating features are features that disseparate the label Y from the context C. So in the disseparation is a graphical criterion that we use, especially in computer science, but also in other fields. And the disseparation is a criterion that you can apply to the graph to read conditional dependencies. So what this means is we want, sorry, a second. We want features that make Y independent of C. So if we have a set of features S, which is a subset of all the covariates, we search for S such that Y is independent of C given S. This is what we're going to look for. And we can reason about this if we know the true causal graph with the graph. So I'm going to tell you right now, because I cannot explain this separation in less than 20 minutes of that talk and other things. So I'm just going to tell you, so trust me, but otherwise you can check. This is called disseparation. And it's a criterion from Pearl and others. For example, you can check his, I think, causality, the new edition of the causality book. But anyway, so what we're trying to search for, we're trying to see if X1 is a good predictor for Y, such that in a new domain, it would still be stable. And we can see that Y is disseparated from C when we condition X1. And the reasoning is there is a path from X1 to Y. And when we condition X1, this path is blocked. And then there is another path from Y through X2 to C, which is blocked if we don't take X2. So this would be something called a collider bias. So X1, you can trust me on this, we can read from the graph. It's a feature that would be safe in a new domain. And I'm also going to show you a plot. In the plot, we have Y here, X1 here. The green data are the data from the sources. The blue data are the data from the target. We only use the sources to train, let's say, our linear model. And as you can see, our linear model more or less works also well for the target. And so in a sense, this means that the conditional distribution of Y given X1 and C0, so this is the data in the source domain, is the same as the conditional distribution of Y given X1 given C1. So this is in the target domain. And so this is essentially, if you know, if you can use the definition of conditional dependence in this setting, this is what you would get. So with this operation, we know x1 is a good feature. We can try now x2 here. And now x2 is not a good feature for two reasons. First, because there is a path from C to Y that it's not blocked if we don't take x2. Second part, there is a path from C to Y that gets activated when we take x2 because x2 is a collider. So collider is a variable which has two incoming edges. So this is the plot of trying to predict Y from x2. And this is our source data. And this is, let's say, the linear model we would get. And this is instead the target data. So you can say we'd get horrible results in the target data, potentially very bad. And this is because I constructed the example so that this would be very bad. But in general, we just know the distribution is different. So there are also other cases in which actually by chance it could be very close. Okay. And this is essentially, I'm telling you, there is a way to read it if you know the causal graph through a criterion which is well known. And so in general, if something is, if a set of features separates Y from the context variable, then we have a bounded generalization error. Otherwise, we have an unbounded large error. And so I think this may be, I'm going to skip this question, but essentially the idea is that if you know this separation, you would know that Y and C are still separated if we take x1 and also if we take x3. So we can take descendants of the label. There's nothing wrong with that. We're just going to take descendants, which also shift in the new domain. And this is what sometimes people call collider bias in other fields. So these are all things that are pretty well known. It's just a different way to look at them. Okay. And so, and if you want to discuss, so if you now you have an edge from C also to x3, now x3 is not anymore going to be a good predictor set. So then you should actually only use x1. And so knowing this separation allows us to reason about that. And then what turns out is that if you have edges to every other variable except Y, then you want to take the causal parents. And this is a bit related to some of the work that Peter, Nikolai, and Jonas have been doing on invariant causal prediction. Okay. So I'm going to skip that. I think maybe I'm going to give you an intuition of these ideas, but if you want, we can discuss later if there is time. I think we're a bit short on time. But just to give you an idea, knowing this separation allows us to reason about some things which people do in machine learning, which if you know how this separation works, you wouldn't do these mistakes. So one mistake is that if something is invariant across some environments, then people might assume then it's definitely causal, right? It's invariant across some environments. And, obviously this is an example and we can show it with the separations we can read from the graph in which, for example, so Y is independent of C given both x1 and x2, independent or disseparated in this graph. And therefore, if you're unlucky and you think x1 and x2 have a stable relationship to Y in different domains, we would think that both x1 and x2 are parents and x2 is not a parent. And so invariant across many different data sets is not enough. And that's why other, like Peter and others, have developed this other method called invariant causal prediction. And then what you want to do there is you would do the intersection of all these separating sets. And then you would take the intersection of x1 and x2, and then you would find x1. So this is a simplification. So the paper is much more complex, but just to show you that the simplification also, like the reasoning can be also applied to the simplification. Okay, so this is one example. I'm going to skip that. And another part is you can think sometimes that we're fine with taking the causal parents. So sometimes people in machine learning think we'll just find whatever the causal factors are of this label, and then we'll be fine forever. And this is only partially true. So you need to find all of them. If you only find observed parents, because for example, there is a latent variable here also causing Y, then you may get that if you're trying to take only x2, which is one of the parents, x2 is not enough to disseparate C from Y. And the reasoning is that it blocks this path, but there is another path through H where x2 is a collider, which is now suddenly open. So if you know this separation, you can read these things relatively easily. Okay, and so I'm going to say that causality, and that's why I call it causality-inspired. Causality is in the terms of finding the causal parents is not necessary for distribution shift. And it's also not sufficient in this case. And instead, what I care about specifically in these works is more about which are the conditional dependencies that hold, or these separations. And these separations allow me to reason about conditional dependencies. So just to give you an idea, very quickly, because of the time, I'm going to tell you what happens when we don't know the graph. So we have a slightly more complicated example. So now we have unsupervised domain adaptation, and we also have multiple sources, which just means we have multiple source domains. So now we have two types of mice for which we have the data, and another type for which we don't have the data. So that's our target domain. And then in this work, domain adaptation by using causal inference to predict invariant conditional distributions, in which the title essentially says everything we did. But the idea was we're going to add not one, but two context variables in this case. So one per domain, actually, almost like a one-hot encoding. So we have C1 will be only one in the second domain, and C2 will be only one in the first domain. So, so this would be, let's say, domain 1. So if we start counting from 0, 1, and 2. Okay. And then what we care about is we don't care about the conditional independencies between Y and the whole domain variable, but only C1. So we have a way to disentangle the target domain from the rest. And so we can show that we can represent this graph with an unknown shared graph. And the way we do it is through something we call joint causal inference. So in this case, we can add these context variables, as I mentioned, and then we will try to learn a graph that is joint across all distributions. So these are examples of different graphs. And then what I'm going to do is I'm going to convert the samples by adding these C1 and C2 as before. And then what I can do is from C1 and C2, I can just pretend that these are only observational data. And there are so many methods on learning causal graphs from observational data. For example, there is a method called PC, there is a method called FCI, etc. And so on this data, we can, for example, then do some conditional independencies, and we just consider C1 and C2 as normal variables. They're not technically random variables, but we will consider them as such. So we can do conditional independence tests, and then we can learn a set of graphs that fit the data. Okay. And so we're going back to domain adaptation. So we can use the ideas of joint causal inference, but now we also have some missing data. So we'll need to do something a bit more complicated. So the first part, which I was already hinting about before, is we will search for separating features that separate Y from the target context variable. So instead of having just one context, we'll have separately one target. We'll have to have a lot of assumptions, which are under the hood. So I have them in the end of the slides for Niklas if he has questions, but otherwise, I think for now, let's just say there are some assumptions that we need. These assumptions can be summarized to the fact that there is not an edge directly to Y, and there are no extra dependencies involving Y in the target domain. And then we're going to take all of the data that we can. We're going to do all conditional dependencies that we can. So for example, where Y is involved, we'll have to assume that we're not taking any data. So we're going to only use this data here. But for other variables like X1 and X2, we can use all of the data. We use these tests in a constraint-based method, and we'll find all the graphs that fit this data. And then now that we have this representation in which these dotted edges represent graphs, edges which cannot be there, we'll try to find, we'll try to use this separation criterion that we have to find sets that separate C1 from Y. And in this case, we can see, if you knew the separation, you could see that X1 would be a good set. So we're going to automatize this instead of doing it by hand, and we're going to use a theorem prover. So that was the idea of our method there. And in that work, we had a query. We wanted to know, is X1 a separating set? We had some assumptions, and this is the technical part. We tested some conditional independencies from data. We use a logic encoding of this separation, and then we throw everything in the theorem prover, and the theorem prover tells us, oh, I can prove this is separating, which means it's separating all the graphs that fit the data. Or I can prove it's not separating. It means it's not separating all of the graphs that fit the data, or it's not identifiable. So these are the two identifiable cases. And sometimes the theorem prover can also say, I don't know. And then we can choose maybe to be very conservative and only select things that we can prove are separating. So in this case, we can guarantee that there will be a bounded generalization error. So this is what we had proposed in this work. And we had like a very simple brute force algorithm in which we tested many sets of features, for example, selected by random forests, but there were also some limitations. So first, the good part. The good part is we didn't find the graph. We don't care about the graph. We care about these separations or conditional dependencies. We did use the graph as some kind of inductive bias to help the theorem prove and reason about it, but we don't care about the graph necessarily. But there are at least three triumvirate of big limitations. One really big one is the scalability. So the method, was very nice, but it can work with 4 or 5 variables and a few different domains. So it's not really a method you could deploy. There are also some other limitations. In this work, we had done only feature selection. And also, as I slightly hinted before, so we were only checking if the distribution changes, but it could change very slightly. So it was a very conservative approach. And also maybe some of these methods could be, some of the features could be good, but we didn't really use them because we thought they probably would be maybe unsafe. And so this is some of the limitations. We had some other work. So one work that addresses the scalability limitation is some of the work we did recently. I'm going to give you a very short summary because of the time, but just to give you an idea, we applied these ideas in transfer reinforcement learning, in which we were trying to learn how to play Pong in different settings, in which we were changing the colors, rotating Pong. And then we learned a graph in which some parts were similar to the context variables, and these parts were similar to the normal variables, the system variables we had before. We had a version with symbolic inputs, so we know the positions of things. We had a version from images, and then it starts to get quite more fuzzy what these different latent variables are, but it still was useful. And then what we did is on the source domains, we estimated the graph, then did some optimizations, and then learned an optimal policy. And then in the target domain, in which there was a new value for a type of, let's say, change that we have already seen. So let's say a new value for a rotation. Then very quickly, we will try to estimate the latent variable theta that represents, for example, the parameter of the rotation. And we could do it very quickly because we assume it's low dimensional. And then we could apply the policy pi to this new target domain. And it seemed to work. And there were many simplifying assumptions, but the idea was similar to the one I presented before, just much more simplified to make it actually scalable. And here are some results, but the idea is we have a version of our method which doesn't estimate the graph, with the graph is substantially better. So I'm not going to say because of the graph, but I'm going to say at least thanks to the graph, this was better. And we also apply very similar ideas to non-stationary reinforcement learning. So in which, for example, you have an agent which is trying to learn how to run, and there is a non-stationary wind that's going against it. So you need to estimate the wind and this kind of settings. So it was a very similar setting. So as you can see, there is always a part in which we have something that represents the domain. And in this case, the domain can also vary in time, and something that represents the system. And we estimate this graph through something a bit more complicated that I'm not going to explain. And then again, our method is the red one. The return is reinforcement learning positive, so higher is better. Our method works better than other methods, at least these methods. And then in the ablation studies, when we switch off things, we see that the biggest contribution, which is the points I'm trying to draw, is because of the graph. So the graph seems to help a lot. So these are my conclusions. The first part, I talk about the separation very quickly, but just as graphical models and the separation are a way to reason about imbalances and distribution shift. And I just wanted to say, it's not my observation. People have known this for a while. And this works even if you don't know the causal graph. And in our work, we also work with what happens in missing data, zero-shot settings. And in our work, we didn't care about finding the causal graph. We cared about these missing conditional dependencies. And then in the end, I kind of ran through a few slides on the idea that maybe sometimes ideas from causality can be also useful for some settings, even if we cannot guarantee that we're learning the true causal variables or the true causal graph. So that's it. Shall I give you back the... Okay, I'll try to give back to Andrej, the host.
Thanks. Thank you.
Yep.
Next presentation. Xinwei.
Okay, great. Thanks, Sarah, and once again, Zijian, for the two fantastic talks. So maybe we can take questions at the end. So now let's welcome Niklas to give our discussion.
Okay, thanks. Can you maybe also give me the host? And then we'll see if it works this time. I tried last time I got kicked out, but let's see. Can you see?
Yeah, perfect.
Yeah. Great, excellent. So thanks both of you guys for these very nice talks. So I will now discuss this a bit, and so for this discussion, I kind of thought of I would try to put both these two methods into kind of the same notation and framework, and then at the end I have a bunch of questions, but we can see how this goes. So I'm very high level in this discussion, so I'll just be we'll see when it makes sense what I'm saying. Good. So first, regarding this problem description, just to shortly repeat this again. So the setting that we're thinking of, so kind of in both talks, is that we have multiple environments that we're observing. And then I kind of call these in terms of the distributions, right? So we're thinking about observing some predictor covariates and the response variable y, and these in different distributions depending on this little index E1 to EL. So these are our observed environments. And then we have here this potentially partially observed test environment where we want to say something. And what we want to say is kind of different across these two talks. So in Sarah's talk, what we wanted to do was prediction. So here I kind of write down out of distribution generalization. So this would be, we know nothing in the test environment, or kind of the setting that Sarah looked at was kind of more this domain adaptation setting where we observe also the covariates in the test setting, for example. In the second, or in the first talk actually, so there we were looking actually at something different, right? So there we were kind of interested not so much in doing prediction, but we were interested in kind of finding these effects that are somehow reproducible across studies. And I would argue at least that in some sense, we think that these are reasonable quantities because they have a certain type of causal proxy meaning that I will explain in a little bit. Good. So just to make this a little bit more precise, so we can, I think, phrase both of these. So this is now very general. So we just assume we have some causal model that is kind of a model over our response y and the covariates x. And this causal model generates now the distributions that we're observing and the one that we want to test. And now we have different e's here. And these e's are kind of the environments or experiments that we're thinking about. And these we model somehow as interventions in this causal model. So I will go with an example in a second if this does not yet make sense. But essentially what we have is that we have some training observations and some test observations. And now I need to make some type of assumptions on the system in order for this to be somehow sensible, right? So and the way I would make these assumptions on the system, or kind of to relate somehow these different distributions between each other, one way of doing that is constraining kind of the causal model and also constraining the interventions that I allow. So what you can think about here, for example, the causal model, if I only consider like linear structural causal models and only allow a certain set of interventions, then maybe these distributions cannot be particularly far apart. But if I say like I allow like completely like arbitrary causal models and any type of intervention on the system, then obviously there's nothing that I can say because there's no relation between these distributions that I can utilize in itself. And now this is kind of the very important point, is that in general, and this is kind of common in causality, somehow the thing that we want to reason about, which is now this distribution in the test environment, this is somehow not in general, it's not identifiable from the observations that we've seen, even if we see like part of the covariate distribution under the test. So this might still not be identifiable. So what we're going to do is, and this is also what Sara nicely said, is we're going to only use partial causality, somehow to leverage only the thing that we want to solve, the task at hand. So either prediction or estimating somehow interesting effects, okay? And now just one simple example, I think, to illustrate this. I'll make this somewhat short. So I will use here now a structural causal model. Essentially, this can be any causal model. We'll model interventional distributions. So here we're thinking about structural causal model. That means like every variable that we're modeling, every causal variable will have a structural equation, and this will induce a causal graph as well. And now we can also constrain kind of the set of interventions that we look at. And here I will only look at interventions on variable x1 and variable x2. And an intervention on a variable in this causal model just means that I replace the structural equation in a certain way that I can also constrain if I like. So now if we do this, then what I want to say now is that we consider now a few observational environments, and on each environment I can do now consider plainly this environment, and I can estimate an OLS effect. So I'm looking at a linear structural causal model, so this might be a reasonable quantity that I can look at in this setting. And this is now the population OLS, and now I'm just going to look at the first two coordinates of this thing. This is also kind of the plot that we saw in Zijian's talk at the beginning. So this is now should become familiar. So what I'm going to look at now, so the first environment is generated kind of by this intervention. So it's just kind of a stronger variance on this x1, and otherwise nothing changes. This gives me this population OLS. And now I add a second point where I get another data set, which is under a different intervention. And here kind of the intervention now also affects this variable x2 by kind of reducing the effect of y onto x2. So this will in particular mean that kind of the OLS regression coefficient, it will not be as good, as useful for explaining y as it was in the original environment, right? So now this goes down. And now comes kind of the interesting part to this whole setting. So now we will be thinking about a test distribution. So this kind of the E star that I was saying before. And here we kind of now need to make somehow an assumption that is somehow reasonable. And now, so before I said, okay, so we're constraining ourselves to having like interventions on the same set of variables now. So we want to intervene on these. But maybe we do not want to allow for all types of interventions. And now in the two talks that we saw, I would argue that we kind of saw also two types of ways to attack this problem. So the first one here is maybe this Maximin effect. So here what we do is we kind of say that the test distribution is somehow no worse. And I know this is now very vague what this means, but essentially what I mean by this is that kind of what we've seen kind of is kind of as bad as it's going to get in terms of the effects that we see. This means that kind of this convex hull that we saw described, so our regression coefficient in this linear case will lie somewhere in the convex hull of these two things. And what we saw is that there was no effect kind of on beta 1, because this is here apparent, so the interventions really had no effect on kind of beta 1, but beta 2 it moved around, right? And now the Maximin assumption is that the new distribution will be somewhere within this span. And the second set here would be this causal invariance, what I would call this, and these are kind of the separating sets from the second talk that we saw. And here we kind of assume that, so we're literally just saying same variables are going to be intervened on, but these can be basically arbitrarily strong, but somehow only in the same directions that we've seen. So same interventions that we're looking at. And this means kind of, so we saw that the effect never really hit beta 1. And so we're looking at populations. So we're kind of assuming we're estimating this here appropriately well. But in that case, kind of we could expect like arbitrarily strong changes onto the beta 2. And this is kind of what happens. So if you get, for example, in the test environment here, a negative effect on your second parameter, then this can be, in the linear case here, an arbitrarily harmful kind of effect if this effect starts getting linear and I'm predicting something that is positive, right? Good. Yes. And now, so once we decided basically on what type of interventions we allow, then we somehow need to say, so what is the quantity we want to estimate now? And here both frameworks can, I think, nicely be phrased kind of in the same type of setting where we just assume basically we go with the worst case optimal setting. So this is now phrased exactly the opposite way around as in the first talk. But so essentially we're thinking we have here this risk function over the parameter for some distribution that I'm looking at. And this distribution is now in this class that I'm looking at. And I want kind of the worst case of the distributions that I allow in my test. And then I want to be optimal under that setting. So in the Maximin setting, this means kind of, we're thinking about this thing here as being, this calligraphic PI as being kind of the convex hull of the observed distributions. PE, and we're thinking about this R P beta term here as the negative explained variance, and then you kind of get the Maximin effect out of this. And similarly, if you now look at the causal invariance thing or Sara's talk, then what you're looking at kind of is you're looking at all these distributions, again, a class of distributions, and you're guarding yourself against any distribution kind of that satisfies the same invariances that you've seen in the original data. And the prediction error here kind of is the mean squared error. Good, and maybe some remarks on this. And this also what I was going towards my first question then, is that if we have this choice, I think kind of for both of these methods and all of these causal inspired methods that go in this direction, you always have a bit of this trade-off of how to choose basically now what interventions you expect in the test distribution, because you would ideally like to choose this as small as possible, because if you choose it too large, you will be starting to become super conservative, because choosing it very large means there's not a whole lot of information that I can use from the data that I've seen to transfer to the test, right? So this is kind of, there's always this trade-off, and if I make it too small, then I will, of course, not guard against kind of the interventions that I'm seeing. And so I think it would be nice to think a bit about, and I've also thought a bit about this, but I've never really come to a proper conclusion because it always kind of depends, I think, very much on the setting that you look at. But if there's ways of kind of, instead of always looking at this worst case optimal, whether there's somehow a way of doing something a little bit more in between or nuanced. Good. And with that, I come to my questions. And so maybe we can, so I have also then a group of questions regarding for both of you, but maybe we start with this first one. So do one of you want to talk a bit about what you think about, or so maybe first you can say whether you think this is a reasonable setup that I proposed, and whether you think that it's valuable to think about kind of going beyond the worst case optimal setting. Either of you can start, if you like.
Yeah, maybe I can start.
Yes,
so
thanks.
Yeah, I think this is very valuable. So one thing I can mention is when I try this real data analysis, I actually have 46 media I can choose. And
Yes.
That's kind of like, you can imagine the more media, I mean, I include means like the more source population we include, and this means more heterogeneous. Okay.
Yes.
And so that's also related to this PI. Like if we got a lot of source population, then the PI can be huge. because they basically all of the regression vector they spread around the whole parameter space. So what I observe is like in that case, it's just not useful, because if I include too many sources, like especially those at east, like people can manipulate. It's not like human being, we cannot do much, but for east, like those scientists, they can create their own environment. So from that sense, is exactly your point. Like if they make the PI too big, then basically all of the prediction model is null model. So they just construct a null model, and that'll be the best for all. So I think it's definitely very important to try to do the trial PI. So just have two remarks. Yeah, go ahead.
So how did you actually do? So did you, in your simulations that you also showed before, so you just restricted kind of the settings that you looked at, or so how did you?
Yeah, I basically like try different combinations. Some cases I make the regression vectors that are similar. But of course, sometimes I make the sum of the coefficient to scatter around 0 to have some heterogeneity.
Yes.
Yeah.
Okay.
But I think the good thing is in practice I track with some domain scientists like Tianxi. So she told me that in practice those we know that the relationship, they're heterogeneous, but they are somehow similar. So I think that's kind of the first response. It's kind of hopeful, at least in some reasonable setting, like in they handling the electronic health record data for human being. So I think those relationships, they are more similar. Like from different countries, definitely they have heterogeneity, but we're all human beings, so it's somehow similar. So no matter like what kind of race, what kind of like a population, like subpopulation we are from, like there are some similarity. I think that's the first thing. Like let's say imagine all of the regressions, like they're scattered around some true value, but they're not exactly the same. So in that case, like this kind of PI is also not that large. Because like they are scattered around some true value. And another quick remark is like we have some recent work coming up soon, like talking about we can shrinking the PI. So the PI doesn't have to be the whole simplex. It doesn't have to be the convex hull. It can be a sub-convex set, a small one shrinking to 0. So there still could be some result obtained.
But so does that mean you scale kind of the convex hull, or does it mean you kind of
it means like say
combinations of the
different combinations. Say we look at all kinds of convex combination, but they have to converge to the truth, or they have to lie in a very small convex hull. Converging to 0. Yeah.
Yes.
Yeah. So that's something maybe like I mean, it has an issue. Like, what if it doesn't contain the P star? It could be the valid question, but I would say like at least I give users some flexibility, like they can choose the uncertainty class. Yeah.
That's interesting.
Yeah.
Oh, sorry. I just wanted also to have like a short answer. I think you're absolutely right. I think in our work we don't really consider this, and we should. But I do think that actually I had the impression that there were more recent works, not ours, obviously, but maybe still in Copenhagen. I had the impression that they were also starting to consider different types of parametric assumptions, in which then you could maybe move from the worst case to maybe more the average case. And I thought in a sense also the anchor regression work in a sense is also kind of reducing the space of PIs to be like maybe to not necessarily have to focus on the worst case. What do you think, Niklas?
I mean, yes. Okay. Can you still hear me?
Yes.
Okay, good. I'm always a bit nervous with my Zoom. Okay, so maybe one question that I think goes related, because this is a question that I have on here. I think for you, Sir, this is this last one here. So can the information, so I think, so you use basically the information in the test distribution from the covariates, right? To find also these d-separation. Have you also thought about using this more explicitly to update kind of your predictor somehow in a less conservative way? Because there I think one could use, because then you know somehow something about the strength of the intervention that you're expecting in the test distribution, I believe, right?
Yeah, Totally makes sense. Totally have thought about it, and people have told me to think about it, but I still haven't done it. So definitely still open problem. So good point. Still open.
Okay, yes, I'm looking forward to if you find something out there. I think this is a very interesting setting to analyze. Good. Should we go over a little bit more questions? I don't know how much time we actually have, but maybe a bit more.
Yes, maybe. Yeah.
Can I
Niklas,
ask
if you just put the questions,
and then we can also open it up to the public. I don't want to take all your time. But maybe, Zijian, if you can say something about this. So this first one, I was just wondering, and this is maybe a naive question, actually. So I didn't have time to go fully into detail into the paper. I only skimmed over it. And I was wondering a bit this instability case that you have, right? So this is one of these cases where somehow the problem arises. Is this somehow actually related to being like a weak instrument? I mean, you're an IV person. So.
Yeah, exactly. It's related to weak IV. So weak IV is like the ratio, the thing they divide by is something close to 0. So that's the weak IV. So I think that's closely related.
Yes,
yeah,
but
weak
IV related. Yeah.
Yeah, but weak IV they have an elegant solution. So they sorry, they can use the stability, the sampling method to solve it, but I think their current way they don't do that. So I kind of tried the sampling idea there is work similar to what they have. So it's definitely related to the weak IV problem.
Yes, I think it would be actually interesting to see whether one can adapt the sampling procedure for the IVs. I don't know if you. But
yeah, I think that'll be interesting. Yeah.
Yes, I agree. Good, and then maybe something I was wondering, and I mean you touched already, I think, on this actually a bit. Is so kind of if one looks, so for example, if I just look at this yeast example that you had, I was wondering because now, I mean, so this Maximin is also often argued for kind of a meta-analysis type approach where you kind of have now these different studies and then you kind of want to compare effects and you say like, okay, so an effect that I see across all studies consistently is somehow a good effect, right? So how do you think about, if you think about now meta-analysis, kind of the Maximin, the pooled estimator, and the individual estimators across these different studies? So how would you relate them, and how large would you expect kind of the confidence intervals to be if I somehow naively combine individual ones or something? I don't know.
I think for the pooled regression, we tried that in the real data. It's interesting. So those like very important SNPs, they always identify. So that's no problem. So very significant SNPs. So the pooled method also works, but it will miss some important SNPs. And to make things worse, they will identify something that's never significant in any of this single environment. So I think the Maximin is kind of identifying something more stable than the pooled analysis, at least in this example. Yeah.
Yes. Okay. So you can really see something in the pooled that is basically actually not in a single one, or what? This can happen?
Yeah. So I just like say pull over all of the source data and run a large regression. I think it's kind of related, kind of equivalent to one of the related, like averaging those environment-wise regressors.
Yes.
They have some equivalence, but But I mean, Maximin, in fact, definitely more stable. So I think my collaborators, like in bioscience, they're very excited about this this Maximin effect.
Yeah. No, I think it is. It seems to have like nice properties, right? So.
Yeah, and for the environment-wise, I just want to mention one thing. So that's why we want to write this medical paper. So they tried this on the co-ed data set, and the result is kind of nice. And also that's the reason I want to keep working on the Maximin, because for one of the data set, one of the environment, so their prediction model building using its own data set is very bad. And then they look at why Maximin improves quite a bit. The reason is Maximin shrinks a lot of this noisy effect near 0 to 0. So that's why it improves. So I think that's the picture I try to show, like it shrinks those environment-wise regression. If they have something scattered around 0, they shrink them to 0. I think that's a beautiful property Peter and Nikolai they have established. That's why it works so well in that real data set.
I think I agree. Okay, maybe to lead over to Sarah's thing. So I mean, so this Maximin. So how useful do you actually think this would be in terms of prediction? Have you looked a bit on this?
Oh, it works well for prediction. So actually, when you give the point, I want to joke about it because I wrote the paper and everyone asked about. So this is a good prediction model. So why do you care about the inference? So that's why I emphasize a bit like why the stable association is important. But as we have discussed, it's not really causal. It has some replicable thing, but it's not really causal. So it's a bit hard to interpret unless like we try to say this is something we can replicate. So it's actually the whole Maximin is for prediction. So if you ask me like if I want to do a talk about prediction or about inference, not considering the paper, I would say prediction. So so yeah. So we have some ongoing.
I was always feeling like it's kind of like I would see it more as kind of a proxy for causality, no? Because you're somehow getting a little bit closer than you would be with just the pooled regression, for example. So I was always thinking, but I know that the thing that I think you also said, this group distributional robust stuff, this is also prediction, right? I think.
Yes. So we have another paper just coming out soon about prediction. So it's all about prediction, no inference. Yeah.
Okay, very good. I also like prediction. And with that, I think we can move then to Sara, the prediction expert. Now the questions that I have are mainly about your last part of the talk, actually. That was very short. So I was wondering a bit, because I've been thinking a bit about these, what it kind of means. So if you have these separating sets, as you call them, then you're kind of thinking about somehow these individual variables as kind of being like causal units, right? So you want the graph on these variables. And now, so in particular, in these last examples that you do, there you have kind of images as inputs or something, and then you kind of learn some features out of these, and then apply the method separately to the features that you get, or is it kind of a joint thing?
So maybe to explain a bit better, I was a bit worried about the time, but in the work we did more recently, we have a simplifying assumption. So instead of actually trying to infer these missing conditional dependencies, we assume that the graph that you have in the source domain, so the joint graph across the source domains, will just stay the same in the target domain. And therefore, we just need to estimate the values of the context parameter. So these context variables, or if you prefer, the theta parameters that we have. So there are some simplifying assumptions there. So it's much easier than what I explained in the beginning. And that's why it's also more scalable and it works better. But I think, conditional dependencies, I'm not sure you would need to have causal factors in the latent space if you just care about things that are separating. But then you need strong assumptions, for example, that whatever you saw already in the source stays the same also in the target.
But you would kind of like to, at least you wanted to map it into a representation where you have a lot of conditional independencies, right? So I could always think about mapping it somehow, and then I have nothing, and then I would get no...
I think I forgot to mention it. We also use like some sparsity. We essentially use some kind of sparsity penalty on the graph. So the graph is very sparse. So in a sense, there are a lot of conditional dependencies. So this is the one I presented today was one line of work in which we don't do causal representation learning. We do causality-inspired, causality-light, whatever you want. But we have another line of work in which we do causal representation learning. And in that case, we can try to learn from videos. So similar to the Pong example, we can try to learn essentially to disentangle the causal factors so that we have a one-to-one mapping between the causal factors and the latent space variables up to point. And then I think there maybe these things would be more interesting. So the analysis I did in the first part of the talk, but we still haven't done it yet either as well. So this is still very ongoing.
Yes, and I guess so if you know, so in this causal representation thing, so what is kind of the identifying factors so what do you use? Because you're
asking how can we identify
all the... I mean, you only even want to identify the invariant, or like separating. So you want to identify something that is good at separating things, I'm assuming.
So in the causal representation learning, that's more maybe similar to ICA or nonlinear ICA, so independent component analysis. So in that case, looks a bit more like classical disentanglement literature. But now the variables are not independent, but they can have dependencies, or they can be like a temporal process. So there is like something like a dynamic Bayesian network, essentially, in the latent space between them. So in that case, I would need to think what are the invariant causal factors, except actually the causes.
Okay, but so basically in this, what you have, you basically get the identifiability from some additional structure on top, I guess.
There are different methods. The method we had worked with, we get identifiability mostly from being able to do interventions. So we need quite some interventions, and we need even to know the labels, so the targets of the interventions. And we're trying to relax that. But there is other work in causal representation learning in which people have other types of assumptions, and then they have sparsity or other types of assumptions, like non-Gaussianity, so going really similar to maybe kind of ICA. And so then they have different settings, but it's a whole completely different line of work.
Cool. Should we open up the questions maybe for the entire audience? So that was all the questions I had, and thanks both of you for very nice talks, I think.
Yes,
thank you
for the discussion.
Exactly.
Invite everybody to contribute to the discussion.
So I can maybe give away the host somehow.
Hopefully we hear now each other. So we invite everybody to discussion. Please just raise your hands and or unmute yourself now and ask any.
Maybe not all at the same time.
You can all at the same time. We will mute you like before.
Actually, can I ask a question?
Sure.
Yeah, I have a question for Sara, and also maybe for Niklas. Sorry, and I've been learning or reading this causal DAG. So one of my question is like, when you do the DAG, like you detect whether it's an error or not. So is it like some consideration about this selection issue? Say it shouldn't be a relation, but or there is a big relation we could not like detect, or we have like detect something that's not really there is not really a relationship, but we detect that. So it's those selection issue a concern.
So Niklas, should I start, and then you can
improve
my answer? Okay, so I'm not sure I understand correctly. So let's assume maybe, like, are you maybe talking about the fact that maybe you have like a very weak effect? So there is maybe if you do a conditional dependence test or dependence test, it doesn't look dependent, something like that? Exactly. Okay. So there are some methods to deal with noisy conditional dependence tests. To be fair, I think none of them are very mainstream. So there are some methods which are based on doing some extra conditional dependence tests. So there are versions of PC and FCI which are called conservative, and they do some extra tests. There are methods which use the Bayesian information criterion, so score-based. So those should be theoretically better at these kind of things. And then there are some other methods which also try to combine score-based and constraint-based approaches. So with conditional dependencies, like Maximin hill climbing, or there are some other methods, for example, that kind of try to give some weights to the conditional dependencies to see how strongly we believe they're true, and then try to do constraint optimization on them. But it's a bit problem of causal discovery, how to actually deal with the fact that conditional dependencies might be noisy. Niklas, do you want to?
Yeah, so I mean, I can also add maybe on to, so I think there's also another way of thinking a bit about this if you think about it in terms of generalization. So if you remember the plot that I did for this Maximin, it was kind of on one line going down, and it kind of the beta 1 coefficient was fixed, right? And now if you have noisy data, so then this will be slightly perturbed around the X1, right? The estimators that you have. And now, so what you would need to estimate in this case, right, is you're saying like, it looks at least like there's no real effect in the X1 direction. And this is kind of then something that goes into your transfer assumption, right? Because I'm saying like, if the effect is somehow not strongly visible across my test environments, if somehow the perturbation is so small that I reject with the test, then I kind of would say that in that case, I just say like, okay, so there is actually no change and I can use this variable. And this is, of course, so now if you allow basically that these are arbitrarily small, you'll run into all types of issues that you cannot detect a small shift. So you're not guarding against this. And then it could be arbitrarily bad again in a new setting. But you're kind of saying that if it's so small, it's very unlikely that it will happen in the new environment. So you kind of can get around it a bit by assuming that it doesn't happen. But this is then the assumption that small effects if there's small shifts or small heterogeneity in the test environments, this also means there's small going towards the test, I think. So this is one way maybe of capturing it, but this is always, as Sara said, I think a big problem in causal inference that goes towards this faithfulness violations, right, in a certain sense. That there's somehow small effects that you just can't see. But, yeah.
Thank you very much. Thank you, both of you.
Thank you.
Would have one or two questions. Hopefully others can also intervene and include in the discussion. For Sara, could your model, can it be used? Does it make sense to use it for any type of the models in the graphical modeling that are used today, say CPDAG, MPDAG, and so on? So can it be used generally for the graphical approaches? And for both speakers, could these approaches be equally used in potential outcome and structural causal models? Thanks.
Okay, I can answer very quickly. So for structural causal models and the standard approaches, the answer is yes. The method is essentially, so we allow for latent confounding, so we can consider things that are not CPDAGs, but PAGs, but they are a bit different because we have some missing data. So they're a bit larger set. So they do work with standard graphical model stuff. With potential outcomes, I'm ignorating potential outcomes. So I think probably, but I would need to think about it and learn more about potential outcomes. So I cannot say anything. No, Zijian.
Oh, I think for my part is a little bit away from causal at the moment. So, in the paper, if you're interested, we use something related like a hypothetical outcome to define one way to define the Maximin effect, but I don't think it's related to the potential outcome. As I mentioned, it doesn't really have a causal meaning at the moment.
Okay.
I think you can kind of put a potential outcome model around also. So the similar thing that I wrote with these things, I think these things you can all define. I think why it doesn't make a whole lot of sense, probably because you don't get like a classical effect or something that you're estimating, but it is a quantity in an interventional distribution in the potential outcome model that you're estimating. So you can define these things also with the potential outcome framework. But I think also relating to Sara stuff is hard to do in the potential outcome framework because you don't want to do graphs, right? So then the graph stuff kind of falls, and this is kind of the main part of the method. So I don't think it would make a lot of sense. And yeah, but so I think generally, yes, you can phrase these all. I don't know whether it adds. Actually, I think there's a certain value in looking at it from both perspectives, actually. But yeah, I think there's a view you could take from the potential outcome framework as well, at least. But I'm also too little into the topic.
Thanks. Thank you. Any other question? Maybe Xinwei, Alex.
I have a very general question. So you have been talking about prediction, and often prediction is understood as a point prediction where you just output a number, say you are in a linear regression setting and you predict the mean. And I'm more coming from the field of probabilistic forecasting, where the forecasts really take the form of a, say, conditional probability distribution of y given x. And I wonder, has any of you thought about somehow extending this framework to providing probability forecasts, which are in some sense robust under distribution shifts, under interventions, or what would you see as somehow the challenges to do something like that?
Yeah, so thank you, thanks Ali for the question. So actually, we are working on like making it to machine learning, but not for probability, but mainly for just for general task, for doing like general FX instead of a linear model. So yeah, that's a worthwhile direction. Like yeah, we know how to do it, but just need to get it out. Yeah, so it's actually the same paper I mentioned to Niklas, the machine learning, general machine learning, and also more accurate information about this the uncertainty class. Yeah, it's definitely it's doable under the current framework. Yeah, thank you.
Thank you. I think in principle you could use it with probabilistic forecasting, because in principle what we are trying to see is which distribution change or not. So we're saying that the distribution of y given x1 doesn't change, so you could. And in general, the fact that it's just probabilistic forecasting doesn't mean that you're robust against shifts, right? So you need something more. So for example, this method can be combined in principle, but just to be clear, again, very good idea. Somebody should do it. I haven't done it. Definitely somebody should do it. Unless maybe Niklas has done it and I don't know about it. So that could be also possible.
No,
Okay.
I mean, I can also say, I think so I mean, essentially, so in particular, if you look at the graphical representation, it's really the distributions that you're saying are invariant, right? So essentially you get this, it's a bit of a question then how accurate you can do this. And I haven't seen a lot of people looking, but I think so I know that some people are looking, for example, at quantiles or something, of like predicting quantiles instead of conditional means with this invariance idea. So that goes, I think, in that direction. But I think there's more to be done, certainly.
Yeah, thank you for all of you. That was interesting, and also interesting to see that you'll find that this is a promising direction.
Further question from the audience or anyone? If not, maybe Xinwei, we conclude. Thank you all. Thank you to the great speakers. Thank you to Niklas for your discussion. And I know that this was live streamed and recorded. It will be accessible online immediately after the webinar on the YoungStatS YouTube channel. What to say, it was a great discussion, hopefully also continues as we discussed earlier with additional webinars in this framework and also related to causal inference. Thank you to all. Xinwei, maybe if you complete or.
Yeah. So thanks, Andrej. I guess thank Zijian, Sara, and Niklas for all the nice talks, discussion, and all the questions and comments. So, and thank everyone for attending this webinar, and hopefully hope to see you in our second webinar. Yeah.
Thanks for organizing.
Thank you.
And,
thank you so much.
Thank you.
Bye.